Morning, guys. Uh, Last time we have seen the Fraunhofer diffraction from single slit. Uh, it is shown in this box, like what we had the intensity distribution, which is like the square of a sinc function, and this is how it will look like. It has a central maximum and several minimas, secondary maximas, etc. And also this will be the intensity pattern if you plot it. And we have seen that in general the UP for Fraunhofer diffraction with certain assumptions that we have taken in the last class, it was like a constant times uh, the area integral of e to the power I k r dA. That's what we have done in the case of a slit, and it is like you integrate. And also during the derivation, we have seen that it is only the aperture that's going to contribute to the intensity pattern at any point in the far field or beyond the slit. And you are substituted for the A, that was L dy, then R was R0 plus ky sine theta, and also this was shear slit, just a length of L and a small breadth or height as B. Now we consider the second example, that's a rectangular aperture. It's actually a generalization of a single slit. Here we consider an aperture, rectangular aperture, with A as the width and B as the height. And you will see that it will look like something like this. Okay, you have a pattern in the horizontal plane and a pattern in the vertical plane. Okay, let's start. This is how this is your intensity pattern for Fraunhofer diffraction. That's the general expression. Now we are going to substitute for dA and e to the power ikr. As we have seen, we will take r as for in both x and y directions as r0 plus x sine theta and r0 plus y sine theta. And since our apertures are assumed to be uniform, it is uniform aperture. There is no face mask or anything else. It has a definite shape, and therefore we can use the product of the two contributions to calculate the field distribution in the far field. What we have is a situation like this. We have light going in, and it is diffracted, and at some point we get we are going to calculate the intensity distribution, and then the derivation is exactly the same as that what we have done last time. I'm not going to explain it a lot. It is two integrals, e to the power iky sine theta and e to the power I kx sine theta integrated over the limits, and it's straightforward. What you will see is here you applied the limits for both cases, and then this will be like 1 by k sine theta is taken as common, and it's e to the power plus I something and e to the power minus I something. It's the same with this one. You get sine kb over 2, and if you substitute all this is what you are going to get. A constant, a modified constant, and we wanted to write it in terms of sinc functions. There are two sinc functions with alpha and beta given by beta equals ka by 2 sine theta, that is in the x direction, and gamma or the horizontal direction, and gamma is kb over 2 sine theta, and therefore the intensity distribution is nothing but this. You have two sinc square functions, one in the x direction, one in the y direction, with the unperturbed intensity I0, and I0 is given by this one, and you get it from here. If you take this as C prime, I0 is C prime star, that is I0. Okay, this is something which you can calculate it using MATLAB. You can substitute the values and calculate this and get an image like this one. Like you have two sinc square functions in going in both directions. This is how you plot the intensity if you plot gamma and beta in two orthogonal directions. I by I0, okay, is given by this one. Okay, two sinc square functions in two directions. Again, you can consider two double slits. Okay, that is maybe something like this one. Two slits. Two identical slits separated by a distance h. Okay, this distance is, let's take it as h, and this width of the slit is, for both, it is b, and it's placed on a screen. I shine it from behind, and you get some intensity distribution on the other side, or the other way around if you want. Okay, here I have shown thetas in the other direction. Okay, this is theta. Okay, and you're going to calculate the intensity distribution at some point p as a result of Fraunhofer diffraction from these two slits, which means you have Fraunhofer diffraction means we have plane wave fronts going into these slits. Okay, again it's straightforward. Here we are going to take okay, the UP is C e to the power IKR dA. That's the same expression that we will use for Fraunhofer diffraction. Since our integration is along one plane, okay, you take you treat this as one-dimensional problem, and therefore the integration is it is like let's take this as the y direction, and therefore the integration will be along the y direction to the power iky, and therefore this integral we can actually split into two, because what we have to do is to integrate over the apertures. Integrate over the apertures. These are the regions of interest that we have seen when we have derived or developed the Fraunhofer formula, that only the open apertures will contribute to the intensity pattern here. This region is not going to contribute, and again the outer regions of that closed surface that we have considered for when we used Green's theorem, uh, that is not going to contribute anything to the point P, and therefore it's only, what are these? Okay, let's take this as 0, then this point is going to be P. Now the h is the distance from the midpoints of the apertures. That means from 0 to the point here, the height will be h. This is going to be h. Just imagine that you translate this line by b by 2. That means it will start h. This arrow will end at the point h, and this is going to be h plus b. And therefore, we only have to consider these two regions, 0 to b and h to h plus b. That's what I have done here. Integral 0 to b e to the power iky sine theta plus h to h plus b e to the iky sine theta. And you do the integration. It is exactly the same as what we have done in the last class, or for aperture and single slit. And if you do the if you do the simplification, you get an extra b, because we wanted to take beta as half kb sine theta, because here you are missing one b, and therefore we use sine beta. And e to the power I gamma, because we have again defined two values. One is half kb sine theta, which depends on the width of the slit. Now you have another one, half kh, that defines the separation between the two apertures, and this is what you will get for UP. And now the irradiance distribution is again the square of that. Okay, I0 sine beta or beta square, that's a sin square function. You know how it is going to look like, and that is shown with the purple color here, that is sine beta or beta. Okay, this is beta. And if you plot gamma or cos square gamma as a function of gamma, then this blue line is what you will get. Okay, and that actually gives you the diffraction pattern. You get the first minima here, and the second minima here. You have a central maximum, the first secondary maximum, and so on. And that intensity distribution due to the diffraction is modulated by this sine beta or beta square. And therefore, in the case of a double slit, you get an intensity distribution cos square gamma modulated by this guy here, a sin square function. And I have calculated, I mean, it's very straightforward to calculate it using MATLAB, and this is how it will look like. Okay, just write a small code. That's why it may be worthwhile if you try and learn MATLAB for simple things like this one. See, the advantage is that you define beta, gamma, then you define sine beta by beta, and then you just simply plot it. Or you can actually write sinc beta in the code, because sinc function is defined. And we'll see as we go down, you can also use many other functions like Bessel without having to write the actual code to plot or to calculate. Okay, that is double slit. The bright fringes appears at gamma equal to, because it is cos square gamma. Gamma equal to 0 means it is 1, that is a bright fringe. Gamma equal to pi is again cos square gamma is equal to 1, that's a bright fringe, and so on. And the angular separation between the fringes is therefore delta gamma equal to pi, because the first minimum appears at pi by 2. See, this is 0 and this is pi by 2, that's the first minimum, and this is the secondary, the first maximum. And therefore the angular separation is pi by 2 plus pi by 2. This is the separation between this and this. Okay, that is about 1.4 because that is 3.14 divided by 2. What is that? 1.67. Is that correct? Okay. And that's the angular separation, that is lambda by h. By varying the slit width, we can actually see, we can actually tailor the angular separation between dark and bright fringes. Or we'll see in the case of gratings how the grating spacing can be used to alter delta theta. And this is very much similar to Young's experiment. Now we go to the third situation. I think that is the fourth one. The circular aperture. Circular aperture, if you have a screen like this rectangular screen and you make a circular aperture over there. Now this circular aperture has a diameter of r. Then at a distance y from the center, you define a strip like this one, and the area of that strip will be the elemental area, that is 2 square root of r square minus y square dy. And if you look from the side, this is what you will get. This is a y sine theta as the path difference between the reference beam and the beam at a distance y from the center of the aperture. And therefore we take y as the variable of integration, and dA is this one, this guy here, and r is the radius of the aperture, and therefore the amplitude distribution, again as we said, I just keep reminding you that this is e to the power I k r dA, and this is how the reference or the integration is now reduced to a single variable y, and therefore r, as we said, r is r0 plus y sine theta, and therefore you can take this out, minus r to plus r to the power. For ease of uh, handling the problem, you define two variables, u and rho. U is y by r, rho is kr sine theta, and that is and therefore e to the power I ky sine theta here will become e to the power I k u r sine theta, and that means e to the power I rho u, and therefore you can substitute e to the power I rho u for this guy here, and you have to substitute for dy, and that is if you have something like this one, dy is du is dy by dr, or that will give you the value of dy, and the limit from we have the limit minus r to plus r for y, and therefore u will be minus 1. Substitute all that into this equation. You have this constant here and an integral like this, and that is now you understand why you have made this substitution, because this becomes a standard integral, and whose value is pi j1 rho over rho, where j1 is the Bessel function of the first kind and order 1, and therefore you can just write it on the other equation. This becomes c pi r square e to the power I k r0 2j1 rho. That's because j1 rho by rho, as rho tends to infinity, is half. And what is rho? Rho was kr sine theta. And therefore, in order to have the right value at rho equal to 0, you put that extra factor 2 there, rho equal to 10. And therefore, the radiance distribution is, if you take again this as C prime, that is C prime times C prime star will give you the intensity, and that is this one, and this is it. Now let's see how it is going to look like in the actual situation. It is very similar to the sin square function in shape, but it has a different value for the zeros. Okay, sorry, this is 0 is here. This is something for actual values I have calculated using MATLAB, and you can see the zeros where the zeros are. These are actual values, the second value, and so on. And if you look at the intensity pattern, this is how it's going to look like. This is the intensity pattern on the screen. You see you have a central bright disk surrounded by a dark fringe. Okay. Surrounded by a dark fringe here, this dark fringe, and then you have a less intense dark bright fringe, and so on. That is the okay. The diffraction pattern is circularly symmetric. Then it has a bright central peak, and we call this an airy disk. Ideally, we like to have the intensity distribution completely concentrated on the airy disk, but due to diffraction, you lose some of this in the bright fringes. We'll see later on, due to a process called apodization, we can actually modify the aperture so that some of this intensity that is distributed now in the secondary maximas can be transferred back into the center. But remember, for a circular aperture, what you get is an airy disk surrounded by secondary maximas, surrounded by concentric circular bands of rapidly diminishing intensity. These are the two important properties of diffraction pattern from a circular aperture. Now let's see where the first minima is. That is roughly about 3.8. Okay, it's just below 4. You can see that, and that is where your zero is. Rho equals 3.832, and therefore the angular radius of the first dark ring can compute from rho equals k r sine theta, and there that is the value of 3.832 divided by k is 2 pi by lambda and r, and if you take 2, if you give 2 to the r, that becomes the diameter, and 3.832 divided by pi will give you 1.22, and that is for small theta is theta. That is the angular separation of the first dark ring is for first dark ring from the center. You can use that to define optical resolution. It is the for that we make a certain clarifications now. The image forms you can is the Fraunhofer diffraction pattern for which the aperture is the lens opening. We use lenses. The simplest image forming device is a lens, or let's say a concave mirror. These are some of the image forming devices, and we can use combination of these to get rid of aberrations and so on. That is probably something that you have on your camera, a combination of lenses. But given I'm saying this is the simplest, or this is the simplest image forming device, and therefore if you consider the aperture of this lens as the or the size of this lens as the aperture, or you can use some real hard apertures here, and therefore in that case this becomes the aperture for the Fraunhofer diffraction pattern. If it's circular, that will make it aperture. And you may have seen that in DSLR cameras, for example, you can adjust apertures. That is what you are doing exactly. You use a circular aperture in front of the lens. Now, the image of a composite object is therefore the superposition of many airy disks. And if that is the case, the resolution will depend on the size of the individual airy disk. and therefore we know that the angular radius of a airy disk is uh, 1.22 lambda by d, and that is the minimum angular separation between two equal point sources such that they can just be resolved. But what happens if you have this situation? The central maximum at this angular separation, the central maximum of one of the sources, okay, or one of the point in the lens, or in this plane, or the each point forms an airy disk, and it will have, let's say, this is your central maximum, this is your first uh, secondary maximum, this is your first bright fringe, and if the angular separation is 1.22 lambda over d, then the central maximum of one of the sources will fall on the first minimum of the other, and that criterion is also called Rayleigh criterion for optical resolution. We know that theta is 1.22 lambda over d is the Rayleigh criterion for optical resolution. Okay, now there is one more topic left on Fraunhofer diffraction. That's multiple slit. That is an extension of single slit, then double slit, then you have n number of slits. Here you have 1 and 2, here you have 1. That I'm going to give this as an assignment. It is after we have done all this, it's a straightforward thing. And also you need to find expressions for the solving power of a grating using Fraunhofer diffraction methods. Okay, thank you.